Hello everyone. Today in this Bode plot part 2, frequency response analysis of control system using Bode plot part 2, we are going to see how to extract the stability using Bode plot, how to tell whether the system is stable or not by seeing the frequency response specifications, frequency domain specifications of the Bode plot. A system is said to be stable when the phase margin is greater than gain margin, and then both the margins, this is one condition. Otherwise, if both phase margin and gain margin are positive, then we can tell the system is stable. The phase margin and gain margin will be extracted from the Bode plot. And then if phase margin is greater than gain margin, otherwise both margins are positive, then the system is said to be stable. The system is said to be marginally stable when phase margin is equal to gain margin or both margins is equals to 0. So we can tell a system is said to be marginally stable. Now, a system is said to be unstable when phase margin is less than gain margin and then any of one margin is negative. Now, I had already said what is a decade and what is an octave in the first part of Bode plot. You can refer that. For a decade, W2, omega 2 is equals to 10 omega 1. For octave, omega 2 is equals to 2 omega 1. Now, phase margin is, we will see what is meant by phase margin, what is meant by gain margin, what is meant by gain crossover frequency, and what is meant by phase crossover frequency, how to extract these four frequency domain specifications after drawing a Bode plot. Suppose if they had given a transfer function without gain, and they had given phase margin, gain margin, phase crossover frequency, gain crossover frequency, how to find the value of K? We will see that. First thing is, let us assume this is the magnitude plot of Bode. This is the magnitude plot of Bode. And then let us assume, initially let us assume this is the phase angle plot of Bode. Now, phase margin is first of all defined. We will see what is meant by phase margin. Phase margin is the phase angle between minus 180 degree line and the phase angle plot at gain crossover frequency. At gain crossover frequency, we know omega is taken along 10 log omega, log 10, log omega to base 10 is taken along the x-axis. So at gain crossover frequency, the angle between phase angle plot and the minus 180 degree line is phase margin. And the gain margin is the magnitude in decibels. That is, this phase margin will be taken from the phase angle plot. The difference between minus 180 degree line and the phase angle plot at gain crossover frequency. So we are taking this from the phase angle plot, phase plot. Then gain margin, that is, you can see formula you can write like this. This is the angle at which omega is equals to omega GC, and then minus 180 plus this. This difference is phase margin. The difference between minus 180 and this one is the phase margin, and gain margin is the magnitude in decibel between 0 dB and the magnitude plot at phase crossover frequency. So this is taken from the magnitude plot. So gain margin is actually the magnitude in decibels, that is the magnitude plot, distance from 0 dB to the magnitude plot at phase crossover frequency. What is meant by gain crossover frequency and what is meant by phase crossover frequency? We will see that now. First of all, gain crossover frequency. Gain crossover frequency means frequency at which the magnitude plot and 0 dB line coincides. Phase crossover frequency means frequency at which phase angle plot and minus 180 degree line coincides. So if you see here, see this is the 0 dB line, this is the 0 dB line, and this is the magnitude plot. Wherever this magnitude plot is coinciding with 0 dB, this point, at this point, the magnitude plot is coinciding with the 0 dB line. So you can draw a vertical line at this point. This is gain crossover frequency. Gain crossover frequency na the coinciding with 0 dB, like 0 dB. Now at this gain crossover frequency, you draw a vertical line. No, the distance between minus 180 line, this is the minus 180 degree line, and the phase angle. This is the phase angle plot, and phase angle plot intersect this line at this point, and this is the minus 180 degree line intersecting this gain crossover frequency. This distance is said to be phase margin. So phase margin is obtained from the gain crossover frequency. In reverse, you can remember phase margin is the margin. Phase margin is the distance between angle, phase difference between the minus 180 degree line and the phase angle plot. That is this. This is the phase margin at gain crossover frequency. How we will get that gain crossover frequency? Gain crossover frequency is the intersection of the magnitude plot with 0 dB. Now, the intersection of phase angle plot with the minus 180 degree line, this is called phase crossover frequency. You can tell omega PC. Phase crossover frequency means intersection of minus 180 degree line and the phase angle plot. So this is the phase crossover frequency. Now, at to phase crossover frequency, again you draw a vertical line. The distance between 0 dB and the magnitude plot at phase crossover frequency is said to be gain margin. This is the gain margin, this distance. This is the gain margin. So, gain margin is obtained from the phase crossover frequency and phase margin is obtained from the gain crossover frequency. Phase margin is obtained by phase margin is the distance between minus 180 degree line and the phase angle plot at gain crossover frequency. Gain crossover frequency is the intersection of magnitude plot and 0 dB line. This is about phase margin. Coming on to gain margin means phase crossover frequency. The distance between 0 dB and the magnitude plot at phase crossover frequency. How to get this phase crossover frequency? Phase crossover frequency is a frequency at which the phase angle plot at the minus 180 degree line coincides. Remember the definitions carefully and understand, don't get confused. So phase margin, gain crossover frequency. Phase margin means gain crossover frequency. Gain margin means at phase crossover frequency. Now you understood after drawing Bode plot how to extract this phase margin, phase crossover frequency, and gain crossover frequency. The important thing is phase margin below 180 degree line, which should be taken as negative phase margin, and above 180 degree line will be taken as positive phase margin. Similarly, gain margin below 0 degree is taken as positive, above 0 is taken as negative. You should remember this carefully. That is, gain margin will be negative below 0 dB. Gain margin is positive below 0 dB and negative above 0 dB line. This is 0 decibel line. Similarly, phase margin now we will tell minus 180 degree, distance from minus 180 degree. No. So, phase margin above minus 180 degree is positive phase margin. And below 180 degree line, it is minus phase margin. So don't get confused. Gain crossover frequency and phase crossover. First thing is the point of intersection of 0 dB line and the magnitude plot will give you gain crossover frequency. Then at gain crossover frequency, we will be finding the phase margin. That is, at gain crossover frequency, we will draw a line and we will find the phase angle difference between minus 180 degrees and the phase angle plot at that will give you the phase margin. Phase margin or phase difference between minus 180 and the phase angle plot. At which point we should find phase difference? At gain crossover frequency. How to obtain gain crossover frequency? It is the point of intersection of magnitude plot and 0 dB. Then gain margin. Gain margin or gain difference. That is magnitude in decibel difference between 0 dB line and magnitude plot. At which point we should find the difference? At phase crossover frequency. How to obtain phase crossover frequency? Phase crossover frequency means phase angle plot and minus 180 degree line coinciding point. That is the phase crossover frequency. So this is about extracting phase crossover frequency, gain crossover frequency, phase margin and gain margin. After drawing the Bode magnitude plot and phase angle plot. Based on this, we can tell the stability. How we will tell the stability? If both the margins are positive, then the system is said to be stable. Otherwise, phase margin is greater than gain margin, then the system is said to be stable. If both are phase margin and gain margin are equal, or both margins are 0, then the system is said to be marginally stable. If phase margin is less than gain margin, or one of them is negative, then the system is said to be unstable. Now, let us see the first problem. First problem, they had given G of S is equal to 10 by S into 1 plus 0.1 S, 1 plus 0.05 S. Actually, here in the question, H of S is equals to 1. So, G of H of S is equals to G of S, which is equals to this. So, the first step, as I had said, is GH of S should be taken. GH of S is G of S into H of S. Since H of S is equals to 1, you can take this transfer function directly. Then, given is a time constant form, that is 1 plus j omega t, 1 plus omega t into s form, 1 plus st form, time constant form. So, you can start. If the given is pole 0 form, you should convert the pole 0 form into time constant form, which I had explained you in the first part of Bode. So you can proceed. Now, first step is G of S is equals to j omega. Replace S with j omega. 10 by j omega into 1 plus 0.1 into j omega plus, into 1 plus 0.05 into j omega. Now, the first step is over. The second step is, as I had explained in the derivation, the Bode plot is obtained by the individual magnitude plot of individual components of the transfer function. So you should extract all the individual components, find the magnitude of each component, draw the magnitude plot of each component, together constitutes the magnitude plot of the system. So I am extracting the components. Remember, while extracting components, first component should be taken. If you had S in the numerator or S in the denominator, you should include that in the first part. That is, the first component should be always some constant K into S. Otherwise, K by S. If S is not there in numerator and denominator, then K. The first component should be always among these three, K or K by S or K into S. Since there is a S in the denominator, I am taking the first component as 10 by j omega. Then the second component is 1 by 1 plus 0.1 j omega. This component. Then the third one is 1 by 1 plus 0.05 j omega. Now, as I had already said, if there is 1 by 1 plus st, the Bode plot will be based on the corner frequency. 1 by 1 plus st now. Below corner frequency, it is a straight line with 0 dB. That is in low frequency range. And above corner frequency, it is high frequency range. And it is in the denominator, 1 by 1 plus st. So, minus 20 dB per decay. So, we should find the corner frequency omega c. Corner frequency formula is 1 by t. See here, compare this with standard transfer function. Standard transfer function is 1 by 1 plus j omega t. If you compare with this, you can get t is equals to 0.1 seconds. So now the corner frequency omega c1 of this term, corner frequency of this term is 1 by t, that is 1 by 0.1, 10 radians per second. So before 10 radians per second, the magnitude plot of this component will be 0 dB, straight line with 0 dB. After 10 radians per second, the magnitude plot of this component will be minus 20 dB per decay, straight line with slope of minus 20 dB per decay. Then the next component is 1 by 1 plus 0.05 j omega. Here, this is the t. Again, we need to find the corner frequency. So 1 by t, 1 by 0.05, which is 20 radian per second. So now we had found out, we had first step, we should find g of s into h of s. Then we should check whether it is in the time constant form or not. Then replace s is equals to j omega. Then extract the components. Find the corner frequency of each component. For first component, there will not be any corner frequency. Why? Because 1 by s. For 1 by s, what is the slope? 1 by s Bode plot. The component 1 by s constitute a Bode plot, Bode magnitude plot of a straight line with minus 20 dB per decay. Now we had completed till here. The next step is draw a table with corner frequency. First row as corner frequency, second row term, third row is individual slope, fourth row is overall slope, and fifth row is frequency range. First, what is the first term? First term is 10 by j omega. So write this 10 by j omega here. Then what is the individual slope of this 10 by j omega? 10 by j omega na 1 by, since for k there is no slope, so you can neglect that term. For 1 by j omega, what is the slope? Minus 20 dB per decay. As I had said, whenever s is in the denominator, minus 20. S in numerator, plus 20. 1 by 1 plus st, minus 20. 1 plus st, plus 20. Then, next term. You write these two, then we will go to next. Since there is no corner frequency for this term, you can keep a hyphen or you can keep dash there. Then the second term is 1 by 1 plus 0.1 j omega. That is 1 by 1 plus st. 1 by 1 plus st, individual slope is minus 20 dB per decay. To understand how I am writing this individual slope, you can refer Bode part 1 video. 1 by 1 plus st individual slope minus 20 dB per decay. And the corner frequency is 10. So write the corner frequency here. Then the third term is 1 by 1 plus 0.05 j omega. It is also similar to 1 by 1 plus st. So the individual slope is minus 20. And then the corner frequency is 20. Now, overall slope. Since this is the first slope, first term, individual slope will be the overall slope. And then frequency range. See, it is starting from some frequency. We don't know. So let us assume the starting frequency is omega s. We can take that as 0.1. 0.1. Let 0.1 be the starting frequency. From here till next, till what? What is the range of frequency for which this minus 20 dB per decay is coming? That is till the next corner frequency. From the beginning of this to starting of next. Starting of next is the corner frequency of the next term. So from starting frequency omega s to 10, it is a straight line with slope of minus 20 dB per decay. So the frequency range is omega s to 10. Now the next term, how to find this overall slope? Overall slope is sum of these two. This one plus this one. Minus 20 plus minus 20 is minus 40. Then this minus 40 dB per decay, from where it is starting? From this corner frequency. That is from 10 it is starting and where it is ending? Till the next corner frequency. So 10 to 20 is the frequency range. With in this frequency range 10 to 20, we had a straight line with slope of minus 40 dB per dk. Then after 20, okay, now we will see here the overall slope is sum of all these three. Otherwise, this minus 40 plus this minus 20. Why? Because this minus 40 already includes these two. So the overall slope is this sum, that is minus 60 dB per dk. Now, this straight line slope minus 60 dB per dk is where it is starting, from the corner frequency 20. Where is it? It is ending. We don't know. So we can fix some omega h, that is upper limit. Omega h is high frequency. Since we can fix the starting frequency and upper limit, starting limit and ending limit, omega h. So the total Bode plot, we had three frequency ranges. From the starting point to 10, it is a straight line with a slope of minus 20 dB per dk. From 10 to 20, it is a straight line with slope of minus 40 dB per dk. From 20 to higher frequency, it is a straight line with slope of minus 60 dB per dk. So now we got the points, but we should know at starting frequency, what is the magnitude of the Bode plot. We know that from starting frequency to 10, it is minus 20 dB per dk straight line. But that straight line starts at which magnitude? We should start, we cannot simply draw a straight line with a magnitude of with a slope of minus 20 dB per dk. It should be joining 2 points. That is, for the frequency of starting frequency, what is the magnitude? And at 10, that is at 10 radians per second, what is the magnitude in decibels? So we need to find the magnitude in decibels at 10 at starting frequency and at 10 radians per second. After finding the magnitude in decibels at these 2 points, you can join that 2 points. And the line joining the magnitude in decibels at these 2 points will be having a slope of minus 20 dB per dk. So now we should find out the magnitude in decibels at all corner frequencies. That is at starting frequency, at 10 radians per second, at 20 radians per second, at a higher frequency. So starting magnitude in decibels, that is magnitude in decibels at starting, at omega s. This omega s is constituted by which term? This omega s is constituted by this 10 by j omega only, no? So magnitude in dB is equals to 20 log 10 by omega. Now I had already said I will be taking the starting frequency as 0.1 for all the graphs. So 10 by 0.1. So 40 dB. So at omega is equals to 0.1. See here. See here, x-axis, I am taking 10 log 10 to the base omega, sorry, log omega to the base 10 on x-axis. And since I have taken omega, this is the 0.1, this is 0.1, and this is the omega s, starting frequency. At 0.1, just now I had calculated the magnitude. How much magnitude I got? I got 40 dB per dk. See, in y-axis, I am taking magnitude in decibels. Magnitude in decibels. Magnitude in decibels. First, I am drawing the magnitude plot. So this is, I am taking this as 40. And here it is 20, here 10 minus 20 minus 40. So at 0.1, I got 40 dB per dk. First point. Now let us check the next point. So I had calculated the magnitude in decibels at starting frequency, starting magnitude. That is at omega s is equal to 0.1. At omega s is equals to 0.1. I got the magnitude as 40 dB. Now I want to get at next corner frequency. What is next corner frequency? 10 is the next corner frequency. So I need to get the corner magnitude at omega is equals to 10 radians per second. listen carefully how to find magnitude at next corner frequency. That is magnitude at 10 radians per second is initial frequency. This is initial frequency. That is, what is initial frequency? Initial magnitude, sorry. This is magnitude. Initial magnitude means the magnitude at before this frequency. Before this, what is the frequency? Omega s. So, omega s, which is equals to 0.1. Whenever we are finding, if you understand this, how we are writing, it will be very useful when we are obtaining the transfer function from the Bode plot. If you want to find magnitude at 10 radians per second, first we should write magnitude at the previous frequency. That is magnitude at 0.1. What is magnitude at 0.1? 40. Just now we had calculated. And then overall slope. This is the overall slope from 0.1 to 10. 0.1 to 10. See what is the overall slope from 0.1 frequency of 0.1 to 10 overall slope? It is minus 20. So first write the previous magnitude in decibels at the previous corner frequency. Then the overall slope from this previous omega s to omega c1 minus 20 log of higher frequency by lower frequency. That is, what is higher frequency in this frequency range? 10. What is lower frequency? Omega s, that is 0.1. So this will give you the magnitude at 10. Now similarly, magnitude at 20. If you see next corner frequency is magnitude at 20. Next corner frequency is 20. So for getting magnitude at 20, first step, magnitude at previous corner frequency. That is magnitude at omega c1, which is equal to 10 radian per second. How much we got? 0 dB. That only I had written here. 0 dB. Then this minus 40 is the overall slope of 10 to 20. That is omega c1 to omega c2. 10 to 20 radians. How much overall slope? Check from the table. See, from 10 to 20 overall slope is minus 40 dB per decade. So the overall slope is minus 40. Log of higher frequency, that is omega c2, 20 by lower frequency, 10. The previous frequency is 10. If you find this, you will get the magnitude at 20, which is minus 12.04 dB. Then, now we had calculated at starting frequency. If you see this frequency range, we calculated at starting frequency, we got 40. At 10, we got 0. At 20, we got minus 12.04. And at higher frequency. So I am fixing the higher frequency as 100. You can take anything. You can take 100, 1000, anything. You can take anything. I am taking it as 100. So at higher frequency, if I want to find what first step, magnitude at previous frequency, that is magnitude at 20 radian per second, that is minus 12.04. Then this minus 60 is the overall slope between 20 to this higher frequency, 20 to omega h overall slope. See, this minus is not formula. If the overall slope is plus 60, you can take plus 60. Since see here from 20 to omega h, it is minus 60. So minus 60, we are writing here, minus 60 log of higher frequency 100 and lower frequency, previous frequency is 20. You got minus 53.97. So now let us plot all these things. The Bode plot. See, first at 0.1 we got 40, we had plotted that. Then next corner frequency is 10. How to fix this? Where is this 10 point now? This is a logarithmic graph. So the dark lines are 0, first 0.1, then 1, then this is 10, this is 100, and this is 1000. These are the dark lines, big lines. Now within this 1 to 10 or 1 to 10 to 100, how to fix now? Next, I will tell you. Okay, now for us corner frequency is 10. At 10, how much we got? We got 0 dB. So corresponding x-axis, where is 0 dB? Here we have the 0 dB. So the corresponding point of, this is the point for magnitude in decibel is 0 dB and corresponding frequency is 10. So we had plotted the second point. Now the next point is 20. Next corner frequency is 20. How to find where is 20 between 10 to 100? Now you just see the graph. This is 10 and this is 100. Here they had given a numbering. See, this is 1 they had given. And here you had 2. 1 means 1 corresponds to 10. Now 2 corresponds to 20. No. So you can take this as 20. This is 30. This is 40. This is 50. This is 60. And this is 70. This is 80. This is 90. And this is 100. Similarly, this is 100 and this is 1000. I said no. So if you want 200 now, 200 is this 2. This is 300, 400 and so on. Now we want this 20. So I am drawing a line at this line. See here. This is 20. This is 20. So at 20, what is the corner frequency? What is the magnitude in decibel? We got minus 12. So this is 0. I had taken x-axis scale, y-axis scale. This is 0. This is minus 20. So this will be minus 10. And this will be minus 12. Zero. This is minus 2, minus 4, minus 6, minus 8, minus 10. And this is minus 12. So you can see at 20, this is the minus 12.04. Now we got this. This is the minus 12.04 at 20. Then higher frequency omega h I had fixed as. I had fixed omega h as 100. So this is 100 now. At omega h 100, how much I got? At omega h is equals to 100 minus 53.97 I got. So see here, this is minus 20, this is minus 40, this is minus 60. So minus 53 will be up below this line, which is here. This is minus 53. So you can draw this minus 53 here. Now I had plotted the points. At 0.1, I got 40 dB. At 10, I got 0 dB. At 20, I got minus 12.04 dB. And at 100, I got 53 dB. So I had plotted the points. Now, from 0.1 to 10, draw a line between these 2 points. And what is the overall slope from 0.1 to 10? From the table, it is minus 20 dB per decade. Then you join this 10 to 20 line. You join a line between this 10 to 20. To 20, what is overall slope? You can see from table. Wait, I will show you table once. See here, from 0.1 to 10, minus 20. From 10 to 20, it is minus 40. From 20 to omega h, it is minus 60. So, from 10 to 20, this is 10, this is 20. 10 to 20, it is minus 40 dB per decade. And from 20 to 100, you join this 20 to 100. This is minus 60 dB per decade. That's it. You had drawn the frequency, the Bode. This is the magnitude plot. This total constitute the magnitude Bode plot. Now we had seen how to draw the magnitude plot. Now let us see how to draw the phase angle plot. As I had already explained you in Bode part 1, how to write the phase angle equation. See, the given transfer function is 10 by s into 1 plus 0.1 s into 1 plus 0.05 s. I had already said in the Bode part 1, you can refer 1 by S corresponds to minus 90 degree. And then this 1 by 1 plus 0.1 S corresponds to minus tan inverse of omega t, that is minus tan inverse of 0.1 t. And this 1 by 1 plus 0.05 S corresponds to minus tan inverse of 0.05 into omega. So you can see minus 90 corresponds to the phase angle of 1 by S. Minus tan inverse of 0.1 omega corresponds to the phase angle of 1 by 1 plus 0.1 S. And then minus tan inverse of 0.05 omega corresponds to the phase angle part of 1 by 1 plus 0.05 S. This is the overall phase angle equation. Now, you can take some values of omega. This is the angle. Now you can take the values. Omega, we had already seen that the corner frequency, that is we had 0.1, 10, 20, 100. For the magnitude plot, you can say take the same values. Otherwise, you can take more also. Substitute this 0.1 in this equation here, in this omega here, as well as here, and obtain the angle what you are getting. That is, you will get minus 90.85. Similarly, you substitute other corner frequencies and get the values of phase angle. Now you had got the phase angles for different frequencies. Now you just plot it in the phase angle curve. I am plotting here. Let me show you. In x-axis, I had taken magnitude in decibels. In the same x-axis, I am taking the phase angle also, that is angle of GH of j omega. This is in degrees. I am taking this as 0 degree. You make sure that they both will not coincide each other. The magnitude and plot and phase angle plot won't cross each other. And this is minus 20 I had taken. Okay. So this is minus 90. And this is minus 180. And this is minus 270 I had taken. And minus 90. And this is minus 180. This is minus 270. If you want to avoid the confusion, actually this minus 60, minus 40, minus 20 are the components corresponds to magnitude curve. This circled one, that is this 0 degree, this circled one corresponds to the coordinates of phase angle. Now, at 0.1, corner frequency of 0.1, what is the phase angle? At 0.1 phase angle, minus 90.85. So, it is starting at this point. This is minus 90, no, so somewhat down. This is minus 90.85. Then, at next corner frequency, what is next? This is the first corner frequency, 0.1. And the next corner frequency is 10. And the next corner frequency is 20. And the next corner frequency is 100. So, at 0.1, it is minus 90.8 here. Then at 10, what is the phase angle we obtained? Minus 161. So, at 10, you can see at 10, this is minus 180. So, somewhat above. This is minus 161. You can plot it and highlight the point. Minus 160. The next corner frequency at 20. What is the value? Minus 198. So at 20, this is 20. This is 180. So just somewhat below. This is minus 190. Then at 100, what we got? 100. 270 we are getting. 252. At 100, we are getting 252. So this is 270, somewhat upside. That is this point. This is 252. Now you had plotted the points, you just join them. You should not join phase angle plot don't join with scale. You can join magnitude plot with scale. Phase angle plot you join freehandly. With freehand you should draw it. And it goes to infinity like this. Okay. Now this is the phase angle plot. Now we had drawn the magnitude plot and phase angle. This is magnitude plot and this is phase angle plot. Now, first step, we should extract this. How to extract? First step, we should extract the frequency domain components as I had already discussed. See frequency domain specifications, phase margin, gain margin, phase crossover frequency, and gain crossover frequency. First, we will extract the frequencies. Gain crossover frequency, now gain difference between 0 dB and magnitude plot. Gain margin, sorry. Gain crossover frequency is a frequency at which, see here, gain crossover frequency is the frequency at which magnitude plot coincides with 0 dB. So let us go to our plot. See, this is the 0 dB line. This is the 0 dB line. This is the 0 dB line. This is the magnitude plot. Magnitude plot coincides with 0 dB at this point. So the frequency corresponding to this point, that is the point at which the magnitude plot and the 0 dB line coincides, is called gain crossover frequency. If you see this x component, that point corresponding x component, it is 10. So the gain crossover frequency is 10. Omega GC is equals to 10. Then phase crossover frequency. Phase crossover frequency is a frequency at which the phase angle plot coincides with minus 180 degree line. Draw a line at the minus 180. See, this is minus 180. I am drawing a line at minus 180. This is minus 180. And this is the phase angle plot. This is phase angle plot. So at this point, they are intersecting at this point. So you can draw a circle here and you can take corresponding frequency. At this point, if you take corresponding frequency, it is this. So it is 14. So gain phase crossover frequency is 14 radians per second. Now we had extracted gain crossover frequency, which is a frequency at which magnitude plot and 0 dB line are coinciding. And we had extracted the phase crossover frequency, which is the frequency at which phase angle plot and minus 180 degree line are coinciding. Now, at gain crossover frequency, draw a straight line. That is at 10, 10, at this 10. At gain crossover frequency, you draw a straight line. Then this straight line, the difference between this minus 180 degree and phase angle plot at gain crossover frequency. See, at gain crossover, this is the gain crossover frequency. This is omega GC. At omega GC, they are not intersecting. We had some distance, this distance. This distance between the phase angle plot and minus 180 degree is called as phase margin. You measure corresponding angle here, and that is the phase margin. You got the phase margin as 18.44 degree. That is the distance between phase angle plot and minus 180 degree line at gain crossover frequency. So now we had obtained the gain crossover frequency omega GC, which is the point of intersection of 0 dB line and magnitude plot, which is 10 radians per second. And we had obtained the phase crossover frequency, which is omega PC, which is point of intersection of minus 180 degree and phase angle plot, which is 14. And we had obtained the phase margin, that is at gain crossover frequency, the phase angle difference between minus 180 and the phase angle plot. Phase margin we had obtained as 18.44 degree. Now let us see gain margin. Gain margin at phase crossover frequency, gain difference between 0 dB line and magnitude plot. So at 14, this is 14 now. At 14, you draw a vertical line. You see this at this point. So this is the 0 dB and this is the magnitude plot. So this is the difference. This is the difference. Now this difference is 8. As I had already said, gain margin whenever measured in the downward direction, it is negative. Gain margin in downward direction of 0 dB is negative. Sorry. Gain margin in the downward direction of 0 dB is positive. Downside of 0 dB is positive. And upside of 0 dB, it is negative. So we had got 8, which is downside of 0 dB. This is 0 dB line. So we should take it as positive 8 plus 8. Phase margin, as I had said, phase margin taken above this minus 180 is positive phase margin. And below this is taken as negative gain margin. See, negative phase margin, as I had already said. Phase margin, it is the minus 180 degree line. Above minus 180 degree line, we will be having positive phase margin. And below minus 180 degree line, we will be having negative phase margin. See here, this minus 180 degree line above only we had. This is the difference. No, this is the difference. So it is plus 18.44. And the gain margin, since we got below, it is minus 18.4. Minus, see here, the gain margin what we had obtained is below. Below gain margin is positive, so plus 8. Even though it is minus, below gain margin positive, above gain margin negative. So it is plus 8 dB. This is dB. 8 plus 8 dB, and this is 18.44 degrees. And these two are in radians frequency, so radians per second. Now, if you see here, phase margin and gain margin both are positive. When phase margin and gain margin both are positive, both the phase margin and gain margin are positive. When both are positive, the system is said to be stable. So the system is said to be, both are positive, system is said to be stable. Now we can check from graph, we got the phase margin and gain margin values. We can even verify this phase margin and gain margin values through calculation. This is additional. What is, let me explain that. What is gain margin? Gain margin is the magnitude. Gain margin is the magnitude at phase crossover frequency. So the magnitude is 20 log of G of 20 log. Okay, this is the magnitude, 20 log GH of J omega at omega is equals to omega PC. You can find the magnitude at omega is equals to omega PC. Magnitude gain margin is the magnitude in decibels at phase crossover frequency. So you can find the gain margin by using, what is the magnitude in decibels? 20 log GH of J omega. GH of J omega. For this, you should keep a model, that is magnitude. In this, you substitute omega is equals to omega PC. That is at phase crossover frequency. Then you will be getting the same answer what we had got. That is what we got gain margin 8. We will get this as 8. Similarly, what is phase margin? Phase margin is the phase difference between minus 180 degree line and the phase angle plot at gain crossover frequency. So, minus 180 degree line plus angle at GH of j omega. You can substitute in this GH of angle of GH of j omega. Omega is equals to omega GC. You will get the same 18 points. You can check this. Now this is how you should draw the phase angle and Bode, phase angle and magnitude plot, thereby drawing the Bode plot. Now, in some problems, you may get the graph like this. You may get the phase angle plot, which does not see here. This is the phase angle plot. And the phase angle plot, you can see here, the phase angle plot is in, does not touching minus, here it will be minus, somewhere it will be minus 180. If you see here, the phase angle plot is not at all touching minus 180 degree. It is just in between 45 to 90. Plus 45 to minus 90. Then how to extract the phase margin, and gain crossover frequency. First thing is gain crossover frequency. Gain crossover frequency is frequency at which the magnitude plot and 0 dB coincides. So this is the magnitude plot and 0. This is the gain crossover frequency. Now you will be getting omega GC. So you can easily get corresponding frequency is omega gain crossover frequency. At gain crossover frequency, the distance between minus 180 line and the phase angle, that is, we don't know where is minus 1. From this point to somewhere minus 180 degree, we don't know. That is phase margin. You can find that phase margin by drawing a minus 180 degree line somewhere down, and you can find this. So you can find the gain crossover frequency and phase margin. Similarly, phase crossover frequency. What is phase crossover frequency? The frequency at which phase angle plot coincides with minus 180. But if you see this, the phase angle plot is not at all coinciding with minus 180. So omega GC is equals to infinity. That's it. Omega GC is equals to infinity. When omega GC is infinity, corresponding gain margin is also infinity. So we can tell we cannot find the gain crossover frequency and what is this? Phase crossover frequency. Phase crossover frequency and gain margin if the phase angle plot does not coincide with minus 180. Similarly, you can solve a problem where the magnitude plot does not coincide with 0 dB. When magnitude plot does not coincide with 0 dB, you will not get the phase margin and gain crossover frequency. Now the next type of problems is, instead of giving a transfer function, what they will give instead? They will be giving a transfer function with k, with gain k. That is, k will be unknown. They won't give the value of gain, but they will give the frequency domain specifications. From the frequency domain specifications given, draw the Bode plot and find the value of k. That is, let me show you a problem and then I will explain the procedure. See, they had given GH of S is equals to k into the transfer function where k is not given. Now, what they had given, draw the Bode plot, find k. If gain margin, they had given the value of gain margin, and then they had given the value of phase margin. From the value of phase margin and gain margin, you should find the value of k. When they had given like this, using Bode plot, how to solve? First step, they had given phase crossover frequency. How to solve? For anything, first step is assume k is equals to 1 and draw the Bode plot. Now, what is phase crossover frequency? Phase crossover frequency. At phase crossover frequency, minus 180 degree and phase angle plot. Phase angle plot will coincide. That is the frequency at which minus 180 degree and phase angle plot coincide. Now, for k is equal to 1, you will draw this. No. You find the, at this omega PC, they have given the omega PC. At that omega PC, if k is really 1, then minus 180 and the phase angle plot coincides. If k is really not equal to 1, then at this omega PC, draw a line, vertical line, and find the phase angle. That is, suppose this is minus 180 degree line, and this is the phase angle plot. Suppose this is the omega PC, given omega PC. If k is really is equals to 1, then what will happen? At omega PC, it should be like this. That is, the graph should come like this. This is the expected. If this is for correct k. This is for correct value of k. If you keep the correct value of k at phase crossover frequency, the phase angle plot and this minus 180 degree line will coincide. But for k is equals to 1, you had drawn initially Bode plot by taking k is equal to 1. So at k is equal to 1, they are not coinciding for the given phase crossover frequency. Find this difference. This difference is x. Now this x should be eliminated. No. So how to eliminate this x? You just equate minus 180 plus x to this phase angle equation. From this, you will get the value of k. In this, you can keep omega is equals to omega PC. Omega is equals to omega PC, and you can find the value of k. This is how to find when given phase crossover frequency. Now, they had given gain crossover frequency. What is meant by gain crossover frequency? Gain crossover frequency is a frequency at which magnitude plot and 0 dB coincides. So, for first, initially, you draw Bode for k is equal to 1 and find the gain crossover frequency of the given Bode. So, at given Bode, the magnitude should be 0. But find the magnitude from the Bode plot. That is, suppose this is the 0 dB line. This is the 0 dB line. This is the 0 dB line. And this is the Bode magnitude plot, what you have got. This is the gain gain crossover frequency. Actually, at gain crossover frequency, the magnitude plot and 0 dB should coincide. But for k is equal to 1, we had drawn for k is equal to 1. So they are not coinciding. K is equals to 1. They are not coinciding. So this should be eliminated. So find this value of x from the graph by drawing a vertical line. Vertical line at the given gain crossover frequency. Now, the value of x should be eliminated. No. So what is this x? 20 log k is equal to x. You equate this 20 log k is equal to x and find the value of k. Then, given gain margin. Gain margin. What is gain margin? Gain margin is difference in the magnitude at phase crossover frequency. So, you find the gain margin for k is equal to 1 system. That is t. Actual gain margin you should get is gamma. So the difference should be eliminated. So equate this difference to 20 log k. Now the final case is given phase margin. For a given phase margin, what is phase margin? Phase difference between minus 180 degree line and phase angle plot at gain crossover frequency. So suppose given phase margin is some y degrees, you just add this y degrees to minus 180 degree, minus 180 plus y. At minus 180 plus y, draw a horizontal line, minus 180 plus y. Actually, at minus 180 plus y, it should be 0. So you draw a vertical line and get the corresponding frequency where this coincides with phase angle plot. This point you extract corresponding frequency. This frequency should be 0. But we are getting not 0, some other value. So you just equate 20 log k is equals to x. So this is how you should find the value of k when they had not given k and they had given gain margin, phase crossover frequency, and gain crossover frequency. In Bode plot, only one type of problem is left. That is, for a given Bode plot, they will give the Bode plot. You should extract the transfer function that we will see in the next video. Thank you.